Is my screen visible?
Yes, sir.
Okay. So in the last class, that is before intervals, we had discussed about the WM concepts and also passive optical coupler, right? Wherein we discussed 2 cross 2 fiber coupler. This block diagram we discussed and all these things, and we did discuss this thing, and we also had a solved a problem on this. The same thing was given in the question paper test also. I think all of you had written, right? Have I answered it or not? Okay, only one has answered.
Yes, sir.
Fine. Okay. Then after that, we were about to discuss all these topics. Okay. This I'll take up. Again, we discussed 2 cross 2 fiber coupler. Similarly, we need to discuss this 2 cross 2 waveguide coupler. Okay. So we need to analyze a 2 cross 2 guided wave coupler. So that can be expressed in a 4 terminal device. So when I discuss Mach Zehnder interferometer, I'll show how it can be expressed into a 4 terminal device. That means it will be having 2 inputs and 2 outputs, as you all know, right? Here you can see 2 inputs as well as 2 outputs, like, okay. So if all the fibers are, it can be expressed, that is in the form of the scattering matrix. So this can be expressed in the form of matrix, that is B is equal to S into A. Fine. So the scattering matrix, which we call it as S here. Okay. So here the input field strength A1 and A2 are the input strength. B will be the B is equal to SA. For example, if we consider what is B, B will be the output field strength. So output field strength will be equivalent to the scattering matrix into the input field strength. So that is expressed in terms of that. Okay, that I'll explain during next topic. Now we'll see the 2 cross 2 waveguide coupler. So what is this 2 cross 2 waveguide coupler? In this diagram, I think you can see clearly. So previous diagram also you have seen, right? It is a 2 cross 2 waveguide, sorry, 2 cross 2 coupler. Here it is a 2 cross 2 waveguide coupler. So basically this diagram, it shows you a type of 2 cross 2 coupler. Here you can see it has got uniformly symmetric device. Here you can see it is symmetric. Both are symmetric, and it has got a parallel. Okay, it has got a parallel guides in the this region. What is this region? This region is the coupling region. So the earlier one which we discussed was, it was a twisted one. So here you can see the uniformly identical parallel guide. Okay. So earlier it was a asymmetric one, where it has one guide wider and the other one is lesser one. Okay. So this it is what I can is compared to your fused type. This waveguide device, this has got an intrinsic wavelength dependency. Where it is that is there, it is in the coupling region. Okay. The degree of interaction between your guide and the team, this can be varied with the width and this, yes, okay, that is the gap. all these things, through which you can control between the guides and also the refractive index, based upon the refractive index also. See, here you can see both are of same this thing. So this is the interactive region. This is the length that we consider. So this region will be the entering region. So in the previous example here also you can see. So this is a tapered region, this is a coupling region, and this is a tapered region, right? Similarly here also this is the coupling region. This will be the tapered region from here to here, and here also. So this is the coupling region. Here it is parallel, and overall this can be controlled through the gap, okay, and the guide width, all this is. So this is what tapering region they have mentioned. So this gap, if you vary this gap, again you can control. Okay. So by seeing this, here the transmission characteristics of this coupler, so it can be expressed in the form of an equation. So that is given by P2 is equal to P naught into sine square of Kz into e to the power of minus Kz. So where the coupling coefficient is K. So K will be equivalent to this much. So just for your reference, I discussed. So these equations you need not to remember and you need not to write in the exam. Okay. Because this is very complicated. So whenever you work and design, so my way of thinking is, if at all, if you work on this and if you are using it for a practical application, then you should use this equation and you can design the things. So, but the thing is, you should know there is a waveguide coupler and it has got some leak. So that's the reason I won't much emphasis on this type of equation, remembering and recalling it. Instead, while designing, you can use it. So next comes the star couplers. So what is this star coupler? Why we need a star coupler? So here in this diagram you can see, okay? So many number of fibers are being twisted, and at the same time, at the many time fibers are being drawn out, right? Similarly, like were earlier 2x2. So here the basic principle of this star coupler is what you need to combine all the powers from these number of inputs. That is here, for example, if here it is 4. Else you can take n inputs. Generally, you can say it is in this thing. So all these powers you need to combine. So these 4 powers will be twisted. Okay, and then drawn out, and then they are drawn out. Okay, so that what happens here, so whatever the input that comes, it will be divided among all these outputs. So here we have got 4 outputs, so it will be divided by 4. Else it will be divided by among this. You will consider, generally it will consider as n cross m. M will be the number of outputs, so it will be divided among m output. So you might ask me, so there are 4 cables and how they are will be twisted. So while manufacturing, only these fibers, the 4 fibers will be drawn and they will be melted, as in the previous class I had told you, I think, that these things will be taken out and then it is melted and made it into a single one. And then they are drawn separately to the required number of levels. Okay, here it is m levels. Okay, so like this is the star coupler, basically design and the principle. So what are the techniques in order to create the star coupler? It is used for fused fibers, gratings, micro optical technologies, and integrated optical technology. So this is basically a fiber fusion techniques. So that is the majorly used, and it is being the popular method for the construction of this in cross and star cup. Okay. In the next diagram, I can show you. So this an example of a 8 cross 8 coupler. So here you have got 8 inputs. So all these 8 inputs will be multiplexed and it will be that means combined and it will be sent here. Okay, it is the other way. Okay, so during large scale fabrication, these devices, there will be difficulty in controlling the responses because there will be a numerous fiber. Okay, all those fibers need to be heated and it needs to be pulled out process. That is what I said, right? So all these fibers need to be heated up and it needs to be pulled out to the required numbers. So this diagram tells you a 4 cross 4 fused coupler. The optical power will be divided, as I said. So the total loss of the devices consists of its splitting loss. There will be a splitting loss plus the excess loss. So the losses incurred in this type will be the combination of the splitting loss as the excess loss. In the 2 cross 2 fiber also coupler also we had discussed. So how the loss will be considered. So here the splitting loss. So splitting loss will be given as minus 10 log 1 by n. Here n will be the number of output powers. Fine. Then the fiber star excess loss. So this fiber star excess loss, there is that means excess loss in the star coupler of the fiber, which is given by 10 log p, 10 log p in divided by summation of I equal to 1 to n p out comma I. So which is that the output of I means you will be having a n number of outputs. So it is a summation of all those. So finally, the losses that is incurred in this star coupler, it is the sum of the splitting loss as well as the excess loss. Okay, so this it is given by for example, I told you a star coupler of 8 cross 8. It is by connecting. So if you want to, if you don't have a coupler of 8 cross 8, and that means like this, all the wires will be drawn and all those will be combined or it is fused, and then later on 8 will be released, right? They are all drawn out. That is one type of technology. So suppose if you have only a 2 cross 2 couplers, then so using those 2 cross 2 couplers, you need to design a star 8 cross 8 coupler is through this technique. So here you can see this is 2 lambda, it is alpha lambda 1 lambda 2. So here it will be multiplied. So this one will be multiplexed with this like so like this. So it is combined here. Okay. Sorry. So if you want to design a 3 dB couplers, so for that we require a n cross n star is nc is equal to n2 into log 2 n. Okay. So and also the splitting loss and excess loss for this type of design, it is given by excess loss is equal to minus 10 log ft into log to the base 2 n. Okay. So the splitting loss for the star again it is given by splitting. So as I said earlier, the total loss will be equal to splitting loss plus this is excess loss. So which will be equal to minus 10 log ft log to the base n, that is the excess loss in this, and the splitting loss. Splitting loss it is given by 10 log 1 by n right here, minus 10 log 1 by n. So the same thing here. So that is that plus this, it is nothing but by n. So which is finally again further simplified into is equal to minus 10 minus 10 into log n into log of ft divided by log 2. This one what we are all separating, that's all. Minus log n, which is equal to minus 10. So 10, it is been reversed. See, log n minus now so minus is being taken inside. So this becomes positive and this becomes negative. So log n is the common. So 1 minus log ft divided by log 2. So log n is common taken out. So 1 by log 2 is 3.322. So 10 into 1 minus 3.322 into log ft into log n. So this shows the log losses, losses, right? So again, with which we can conclude or we can give a remark saying that the loss is dependent upon this n value. So that means what? That means here your loss it increases with respect to your logarithmically with the value of n. So it is not exponentially or it is not directly. So it is increases logarithmically with respect to n. That is what the conclusion which we need to draw. And few problems are there which I think I need not to solve because it is just substituting the values to this ft and n and calculating the excess loss and splitting loss. So which is as same as this problem. So we need not to. I will not be solving. You can substitute and you can see. Fine. So next topic is Mach-Zehnder interferometer. One of you, I think, in your section or other section, I don't know. They have explained about you Mach-Zehnder interferometer. Is that you in your section? Okay. No response. Okay. This wavelength dividend multiplexers. This WDM. This can also be made by making use of this Mach-Zehnder interferometer. So these techniques, in this, it can be either active or a passive. So here we'll look into passive multiplexer, where here the constituents of this Mach-Zehnder, that is a MZ type, we usually say, it basically consists of two cross. So in this here diagram, it tells you about a 2 cross 2 Mach-Zehnder. So it consists of 3 stages. So which are the 3 stages? So an initial 3 dB splitter, okay, or a direction coupler also you can say splitter. So what is the function of that? It is going to split the input signal. Okay, so how it is done? So here it is through the, and also it has got a central section, you can say a phase shifter. So here the length is L. So here it is D, for example, if you consider this is the length D. So here you can see the difference. So it is direct L. So it is, whereas this it is like this in that shape. That means L plus DL. Why the difference in delta L is being created in this phase shifter? Because in order to give a shift, okay, what shift? That is the wavelength dependent phase shift. So there will be a phase shift between these two arms. So when we consider it, there will be a shift between these two arms and another 3 dB coupler, that is at the other end. So finally 3 phases, one 3 dB splitter, one phase shifter, and the other one is a combiner. Okay, with here you can see the arrangement is done in such a way that you'll be splitting the input beam, all these two beams, that is the in one into these two beams. What you will be doing? You'll be splitting, and here you are going to introduce. You'll be introducing a phase shift in one of the path. Either you can create either in this way or in that path. Any one of the path you will be creating that, and finally you will be interfering together at the output and respectively at the other. Okay. That is what the main thing. Here, as I said in the previous topic, that I'll be explaining here. So your scattering, it will be expressed. Expressed is B is equal to SA. B is will be the output, and this is the scattering matrix, and A being the input field strength, D being the output field strength. So here the propagation matrix for the coupler of length D, since it is a 2 cross 2, it is given in the 2 cross 2 matrix, cos KD, J sin KD, cos KD. So K is the coupling coefficient. So we are considering minus 3D P couplers, which divide the equally, which divide them. What is going to do? So it is go here, since we are considering 3 dB couplers, so it is going to divide the power. So you know, when you plot the graph in this thing, so the power will be divided equally. So 2 kd will be equal to pi by 2, so that your M coupler will be 1 by root 2 2 pi, that is pi by 2, cos pi by 2, and so it becomes 1 and jj. Okay, so at the central region, when the signal in the arm, so because of the difference in the length, delta phi, that is, there will be a phase difference between those two. So that is given by 2 pi n1 by lambda into L minus 2 pi n2 by lambda into L plus delta L. See the difference here. Okay, so the phase difference, it will arise either from the different path length, or the it may be through the variation in the refractive index also, whenever both are not same. So here we consider both are of same index, refractive index. Then we can write the equation as delta phi is equal to K into delta L. That means if I will take N1 equal to N2, these two things I will take common, L minus L plus delta L. So only the delta L is going to remain. So K into delta L. So where K will be equal to 2 pi N efficiency, N effective by lambda, that you all know. So finally, if you consider, when there is for a given phase difference, the propagation matrix, this M matrix, it will be given by, so this is the coupler matrix and this is the propagation matrix. This is given by exponential of jk delta L by 2, 0, 0, exponential of minus jk delta L by 2. Okay. So this is again the optical output power, E out 1, E out 2 will be equal to M into E in 1, M in 2. So I said you right. So the input, the output power will be equal to scattering matrix into the input power, right? Input power. So that is what here E out 1, E out 2. What is this E out 1 and E out 2? It is E out 1 and E out 2. That is output. Output power will be equivalent to the input power into the scattering matrix. So that is what we are mentioned. So M is equal to, this is equal to M into E1 into E2. So where M will be equal to M coupler into M, because the three stages are there, right? There are three stages. So coupler, and in between. So if you substitute that, you will be getting sin k. So you need not to worry about all these equations. The thing is, I am explaining to you just to make you understand how this is going to take. So E out 1 will be equal to this much if you substitute all these things. M11, M12, M21, M21. So if you do like this, you are going to get E out 1 and E out 2. So P out 1 will be equal to light density, whereas the square of the field strength. So you will be calculating this. So finally, the length difference in the equivalence R should be, what should be the difference in the length in order to achieve that better expression is delta L is equal to 2n effective divided by 1 lambda 1 minus 1 by lambda 2 to the power of minus 1. Okay, that is 1 by this thing. So which will be equal to C divided by 2n effective into delta V. So delta V is the frequency separation of these two wavelengths. Okay, so here I'll stop. In the next class, I will take the isolators as well as the couplers. Isolators and the couplers. Okay, is there any doubt?